If the solubility product constant for a slightly soluble ionic compound is known, then calculating the molar solubility of that compound can be quite simple. Hi, Mr. B here. In this video I will explain how to use a Ksp expression as well as a Ksp constant to determine the molar solubility of a slightly soluble ionic compound. For compounds that are sparingly soluble, an equilibrium will be established between the solid compound and the ions that are suspended in the aqueous state. To write a proper equilibrium equation for such compounds, for example, calcium fluoride, simply write the following, where calcium fluoride will dissolve to produce calcium cation and 2 fluoride anions. In terms of states of matter, the calcium fluoride, which is sparingly soluble, is written in the solid state. And the ions are clearly suspended in an aqueous solution, so we write a Q. Eventually, the rate of ionization will equal the rate of precipitation, since this is a sparingly soluble salt. So, to indicate this, simply now write a reverse arrow, which indicates that the rates of ionization are now equal to the rate of precipitation. Suppose you're asked to determine the solubility of a slightly or sparingly soluble salt, such as, say, calcium fluoride. To do so, we may perform a Ksp calculation. The Ksp simply indicates how soluble a particular compound may be when placed in water. For calcium fluoride, the Ksp is 4.0 times 10 to the negative 11. And as you can see, there are no units. Ksp values will never possess a unit. However, looking at the exponent, you see that such a small exponent will indicate that very little of this compound will dissolve. To determine exactly how much of the compound will actually dissolve in 1 liter of water at 25 degrees Celsius, simply begin by writing a Ksp expression. A Ksp expression will reflect the stoichiometric relationship between the ions found in solution. To complete the Ksp expression for this particular equilibrium, simply write the following, where the Ksp is equal to the concentration of the cation times the concentration of the anion raised to the second power, which represents the stoichiometric relationship between the calcium cation and the fluoride anion. Now we're all set. Simply now insert the actual value for Ksp and set that equal to the concentrations of the ions. Okay, simple. Let's return to the equilibrium equation, where the concentrations of both the cation and the anion are unknown. So since these concentrations are unknown, we may use X for the cation and 2X for the anion, since according to the stoichiometric relationship, the anion will be twice the concentration of the cation. Now we substitute these X's for the symbols in the brackets. X and 2x squared. Now we may simplify the parentheses, where simplifying the parentheses will give us 4x and 4x squared. Multiplying through will generate the following, where x times 4x squared is equal to 4x cubed. So what do we have so far? Well, we have 4.0 times 10 to the negative 11 is equal to 4x cubed. So to solve for x, we first divide through by 4. So x cubed is equal to 4.0 times 10 to the negative 11 divided by 4. The next step is to clear the exponent by taking the root. So x will equal the cube root of 4.0 times 10 to the negative 11 divided by 4. And of course, the cube root of 4.0 times 10 to the minus 11 divided by 4 is equal to 2.2 times 10 to the minus 4 molar. So the solubility of the compound calcium fluoride is simply 2.2 times 10 to the negative 4 mole per liter of water.